Mount St. Helens is waking again. Seismic swarms ripple beneath the summit in pulses that geologists have never logged before. The ground swells at a rate they argue about in staff meetings, and gas vents that fell silent decades ago are breathing once more. None of this is alarming on its own. Volcanoes are restless things, and this one has stretched and yawned many times since its last great tantrum. But what the monitoring instruments have begun to measure is something scientists have not seen since 1980, and it does not fit a single known pattern of awakening. A volcano that breaks its own rules on the way up does not politely follow the book on the way out. What comes next might not simply erupt, it might rewrite what we think we know about how mountains wake. To understand what makes this mountain different, you have to go back to a morning that changed volcanology forever. May 18th, 1980. May 18th, 1980. 8:32 in the morning. A magnitude 5.1 earthquake shook the north face of Mount St. Helens, and for a few seconds the whole slope seemed to hold its breath. Then, the largest landslide in recorded history peeled away in a single motion, 2.9 cubic kilometers of rock and glacier moving downhill at speeds that outran sound. That landslide did something no one had planned for. It took the pressure off a volcano that had been building toward ruin for 2 months, and the mountain answered by exploding sideways. The blast, initially estimated at half a gigaton of TNT, flattened 600 square kilometers of forest in under a minute, felling trees 28 kilometers from the crater. 57 people were still in that zone when the wall of ash and gas arrived. Some died instantly. Others were found days later, their positions marked only by what they had been carrying. The mountain had not erupted upward. It had erupted outward, along an axis no eruption in the historical record had ever taken. What they found in the wreckage was stranger than the eruption itself. The cryptodome. Where the north flank should have been solid, there was a bulge. For 2 months before the blast, the mountainside had been inflating at a rate of up to 1.8 meters per day, a vast dome of magma pushing outward beneath the surface, hidden from every line of sight until it was almost too late. Volcanologists call this a cryptodome, from the Greek for hidden. A cryptodome never breaks the surface. It lives inside the mountain, a pocket of viscous magma that squeezes the rock around it until something gives, and when something gives, in a peak whose flank has been strained for weeks, the release is not a column of fire, it is a detonation. The 1980 blast was not really an eruption in the classic sense. It was a pressure release, a cork yanked off a bottle that had been shaken for 8 weeks, and the cryptodome turned what should have been a broken slope into a horizontal cannon aimed at everything north of the crater. But that cryptodome was only the surface of something far larger. The plumbing system, beneath the crater, roughly 8 kilometers down, sits a reservoir of molten rock, shaped like an upright bladder, stretching tens of kilometers into the earth. It is not a single balloon of liquid. It is more like a sponge of crystal mush, pockets of melt threaded through cooler, stiffer rock. From that reservoir, magma climbs through a narrow pipe of fractures, and this is where St. Helens gets strange. The conduit does not run straight. It bends, branches, and gets pinched off by cold rock, and the route it takes can change between one eruption and the next. Every volcano has plumbing, but few are as tangled or as stubborn to map as hers. Seismometers trace those pipes only roughly, the way you'd map a house by listening for water in the walls. Most of the system stays invisible, and in 2004, the mountain gave scientists a chance to see inside it. The dome builders. In the fall of 2004, the seismometers had barely stirred for a week, and then magma surfaced almost casually on October 11th, rising beside the old dome where the 1980s conduit had died. Over the next 4 years, the volcano behaved like a different animal entirely. It squeezed. From the vent came a spine of solid dacite, a long, striated fang of rock nicknamed the whaleback for its broad, curved back. It rose like a ship's prow pushing through the crater floor, a few meters a day, and nobody had to run. The instruments watched every centimeter, cameras on the rim, GPS nodes, strain meters buried in the rubble. Small explosions came, puffs of steam and ash, and scientists learned to call them hours in advance, sometimes to the minute. It felt like a system finally understood. After 4 patient years, the eruption ended with a shrug, and the mountain settled back into its long sleep. The confidence it left behind was real and earned. That confidence lasted until the instruments started showing something impossible. The anomaly. But the tremor came back, and it came from the wrong place. It rose from depths that had been quiet, deeper than the chamber the models had drawn, from layers where a sleeping volcano should stay silent. The mountain was speaking from somewhere new. Then the ground began to move in patterns that fitted neither dome building nor the slow swelling of a cryptodome. The surface tilted one way, then sagged another, and the numbers refused to line up with any eruption anyone had watched here before. They had expected a repeat of 2004, a familiar crawl. So the geologists did what geologists do when the instruments lie. They went back to the mountain's own history, asking the rock itself what it has been through, reading the minerals and the bubbles for a chemical thumbprint of something new. To make sense of it, they had to look at what the mountain is made of. Dacite. That rock is called dacite, and it is the whole personality of this mountain in a single word. It is thick, sticky lava, more like cold honey than water, moving slowly if it moves at all. Compare it to the volcanoes of Hawaii, which pour out runny basalt that glides downhill like a red river, gentle enough to walk toward. St. Helens gets no such mercy. Its dacite is so viscous that gas gets trapped inside it, and gas that cannot escape is a pressure cooker waiting for the lid to give. Dacite erupts because it has to. It does not flow, it shatters, and every dome, every spine, every bulge in the crater since 1980 has been built from this same reluctant, gas-filled magma. But the new readings suggest the dacite isn't alone down there anymore. The deep signature. The anomaly doesn't announce itself at the surface. It shows up down at 10 to 15 kilometers, deeper than the chamber anyone has mapped, and it arrives with a frequency pattern that doesn't match the dacite above. Different compositions sing at different pitches, and this one sings like something else entirely. The readings point to basalt, denser and hotter, welling up from the mantle and pressing against the underside of the dacite reservoir from below. Basalt doesn't just sit there, it delivers heat, and heat is exactly what turns a calm pool of viscous magma restless. The two layers begin to exchange, to bleed into one another, and each mingling trace changes what the system will do on the day it finally lets go. Scientists hesitate to say it outright, but the seismic signature is the closest thing they have to a confession from the mountain. If they're right, it would explain why the mountain's behavior has changed. The mixing zone. Imagine what happens when that hot basalt, rising from the reservoir below, finally touches the cool dacite waiting above it. The contact is not gentle. The basalt arrives above 1,100 degrees Celsius, and the dacite hangs a few hundred degrees cooler. Where the two meet, dissolved gas comes out of solution in a rush, water and carbon dioxide flashing into bubbles that have nowhere to go. Pressure climbs from that alone, and it climbs in days, not millennia. This is a known recipe. At Mount Pinatubo in 1991, the same mixing of basalt into dacite helped turn a quiet volcano into one of the largest eruptions of the century. That this is happening now beneath St. Helens is written in the rocks themselves. Zoned crystals, like tree rings, record a sudden pulse of heat arriving months before eruption, a pattern scientists have recognized at other volcanoes right before they let go. But there's a second process at work, one that operates on a slower clock. The edifice. Look at the mountain as an object, an engineered hull. On May 18, 1980, 3 cubic kilometers of its north face simply came off, and what stands here today is not the same volcano. It's a repaired vessel, scarred by a collapse it was never designed to survive. That repair is recent in geologic terms. The flank that slid away left a crater wall 800 meters high, and the rock behind it still carries fractures from that day. Cracks that deepen every time the ground whispers. Tremors pulse through this weakened shell like footsteps on old timber. Volcanologists describe the edifice as a damaged hull holding back immense pressure, and the metaphor isn't decorative. This is a structure whose integrity was compromised once, and whose load, that growing bulge beneath it, has not eased. It keeps adjusting, settling, flexing under a strain it never had to bear before. Every quake is a small test of that hull, a probe of how much more it can take before the fractures link up into something larger. And the fractures are growing. Deformation maps. You can't see the change by eye, but the instruments can. Global positioning stations dot the mountain's flanks, and satellites equipped with radar stitch radar images together so precisely they can map movements of a few millimeters from space. What they measure now, on the north flank, is unmistakable. It is inflating again. The ground is rising a few millimeters every month, a slow breath the mountain can't seem to stop. What makes the data unnerving is not the number, it's the location. The swelling is concentrated in a zone that overlaps the exact failure plane that let go in 1980, the same wedge of rock that slid away in the opening seconds of the blast. Deformation maps render all of this as color, reds creeping outward across the northern slope in monthly frames, each one a little further than the last. The pattern is eerily familiar to anyone who studied the spring of 1980, because the same maps, painted in the same shades of red, were being drawn then. Ground movement does not guarantee an eruption, and inflation can stall or reverse, but the shape of the pattern, the zone involved, the direction of the strain, all match a precedent this volcano has already shown it is willing to follow, which brings scientists back to the question they thought they'd answered in 1980. The lateral blast question. That question is simple and terrible. Could the north flank fail again? Could a second lateral blast obliterate what the first one left standing? The scientists who study this mountain are split down the middle, and the split is worth sitting with, because both sides are looking at the same data. Those who say no point to restabilization. The edifice has had 40 years to settle, and the magma supply feeding this current episode appears to be far smaller than the one that preceded 1980. The plumbing, they argue, simply isn't full enough to generate that kind of force, and the mountain has quietly reinforced its weakest joint. Those who say maybe point to geometry. The flank is still oversteepened, still scarred by the 1980 collapse, and the inflation is still focused on the old failure plane. They don't claim a blast is coming, they claim the mountain has not erased the conditions that made one possible. It has only stored them, and now it is repressurizing that same joint. Two careful readings of the same mountain, and no way yet to tell which is right, because both hinge on something measured in kilometers below the ground, invisible to every satellite and seismometer on the surface. To predict what comes next, they need to know how much magma is down there. Tomography. In 2014, researchers blanketed the mountain and its valleys with more than 6,000 seismographs, a listening net so dense that nearly every tremor became a kind of X-ray. Each earthquake sends its pulse outward, and wherever that pulse slows down, the rock is telling a secret. It is hot, broken, or holding melt. Stack thousands of these paths together, and the mountain grows transparent, and what the image showed was bigger than anyone expected. 10 kilometers down, a chamber 5 to 7 kilometers across, holding up to 20 cubic kilometers of partial melt. Older surveys, built on far fewer stations, had seen only a sliver of this body, and for decades it was easy to believe the mountain was running on small reserves. That is roughly 5 times the volume of everything the volcano has ever erupted in a single event, more than the blast of 1980 by a wide margin. It changes how the mountain's history reads, but there is something else in the same image that shifts it further. The chamber is larger, but that's not what worries them most. The connection, because size alone is not danger. Danger lives in connection, and the tomograms found a connection they had never seen so clearly. Between the deep basalt and the shallow dacite, there rises a column, a few kilometers wide, where seismic waves crawl at the speed of hot, fluid rock. Its edges are crowded with small, deep earthquakes, the long, slow signals that volcanologists read as magma pushing upward through fractures. In 1980, the same signature traced a narrow conduit in the weeks before the mountain came apart. That conduit is open again now, a live pipe running the full height of the system, and it is feeding. The shallow chamber is no longer a closed vault. It has a tap, and that tap is dripping from below. The deeper reservoir is pushing its contents up through the column into the dacite above, and the swarms along the column's edges are not fading, they are tightening, and the rate of movement is accelerating. The timeline problem. That leaves the question nobody can answer cleanly. How long is the delay? When basalt rises toward a silica-rich chamber, the alarm clock can be set almost anywhere. At Eyjafjallajökull in 2010, the fresh magma arrived only hours before the summit blew. Elsewhere, decades pass between intrusion and anything eruptive. Mount St. Helens in 1980 gave 2 months. The first deep tremor sounded on March 20th, and the mountain came apart on May 18th, a span of 59 days. The present unrest has already outlasted that entire countdown without producing an eruption, and no one can say whether the clock is running fast or simply has not started ticking. Every reading of the volcano now splits in 2 directions, and both are uncomfortable. One waits for a larger event, the other for an event the model does not yet see, which means the mountain is either building toward something larger or the system is venting pressure in a way scientists don't yet understand. The gas. Gas escapes before magma does. A volcano's true intentions often surface first as vapor, a chemical whisper carried on the wind long before anything molten moves. So scientists read it like a pulse. Sulfur dioxide, carbon dioxide, helium isotopes, each one tells a different part of the story, and right now, the readings refuse to agree. Carbon dioxide is running elevated, a sign that something deep is stirring. But sulfur dioxide sits surprisingly low, and that mismatch has no easy explanation in the standard model of rising magma. A simple column climbing toward the surface should carry both. Some think the gas is taking a hidden path. The hydrothermal system. The answer might be water. Beneath the mountain's skin runs a hidden web, a labyrinth of hot springs, steaming fumaroles, and underground aquifers threading through old rock. That plumbing can swallow gas and heat, diffusing them sideways into 1,000 invisible channels. What reaches the surface may be only the overflow, a diluted echo of what burns below. Scientists are trying to map it all, one borehole at a time, but the system runs deeper than the drill can reach, and much of it sits folded into rock that refuses to give up its secrets. And there's one part of the system they can't monitor at all. The crater. The crater itself remains the heart of the mystery. 4 decades on, it still steams, still shifts underfoot, still refuses to settle into stillness. In its shadow, a glacier has grown and retreated twice since 1980, a slow breathing of ice over a floor that radiates heat. It is a cauldron of fire and frost, the two stubbornly sharing the same ground. Instruments placed down there rarely survive more than a season. The steam corrodes them, the ice grinds them, the rock swallows them whole. Each visit to the crater floor is a gamble against the mountain's patience. But in 2023, a drone survey captured something new. The fractures. The images showed a pattern no one had seen before. Concentric cracks ringed the crater floor like tree rings, each one tracing a perfect arc around the dome's center. Surveys a few months apart revealed the truth. The cracks were widening, slowly but steadily, month after month. Rock does not crack that way on its own. When the ground beneath a floor is squeezed from one side, cracks run in straight lines, parallel to the force. Concentric rings only form when something pushes straight up from below, stretching the surface in every direction at once. Something beneath the crater is swelling, and the skin is tearing to make room for it. The fractures are more than a warning written in stone. They are plumbing. Every crack is a chimney for heat escaping from below, a vent for steam and gases that would otherwise stay trapped, and the heat flow through those fractures has doubled. The models. Confronted with a signal like that, scientists stop guessing and start building. Computer models now grind through the mountain's anatomy in millions of tiny elements, each one a chunk of rock with its own strength, its own temperature, its own breaking point. Feed in the deformation, the seismicity, the gas readings, and the model tries to bend the edifice until something gives. Other simulations follow the magma itself. They track the ascent of molten rock through a conduit, how fast it rises, how much gas it can shed along the way. Get those parameters even slightly wrong, and the outcome shifts. A dome forms, or a column of ash climbs 24 kilometers into the stratosphere. Every model is an act of faith in a set of numbers, and every assumption is a door left open. Change the viscosity by a few percent, tweak the permeability of a crack, and the mountain behaves entirely differently in the machine. The most recent model produced a result no one expected. The bifurcation. The result was a fork in the road. Mathematically, the system is approaching what physicists call a bifurcation point, a threshold where one path quietly splits into two, and both become equally likely. On one branch, slow, patient dome growth, the way St. Helens eased through 2004 and 2008. On the other, a rapid, explosive eruption. Nothing in the output says which branch the mountain will take. The choice comes down to factors the instruments cannot yet reach: the exact amount of gas held in the magma, the state of the seal overhead, a handful of variables buried kilometers deep in rock, one reading above a line, and the model tips. It is the feeling of standing at a crossing where the signposts are blank, waiting to see which way the current turns, and a bifurcation, once reached, cannot be unreached. So the scientists went looking for a volcano that had already made that choice. Mount Pinatubo. In 1991, the Philippines' Mount Pinatubo gave scientists exactly the case study they needed. The same signature was there, a slug of hot basalt rising up into a cooler, more viscous dacite body, stirring a storm beneath the summit. Pinatubo had a similar lead time to St. Helens, weeks of growing unrest, rumbling swarms, swelling ground. Then, on June 15, it didn't vent gradually. It didn't build a dome. It blew sideways and upward, ejecting 5 cubic kilometers of magma and 20 million tons of sulfur dioxide into the stratosphere, cooling the whole planet by a fraction of a degree. Two volcanoes, the same recipe, opposite endings. The difference came down to how fast magma was being fed in, how strong the mountain's shell was against the pressure building inside it, and how much gas the melt could hold. When the comparison was laid out side by side, the variable that mattered more than the rest stood out alone. The tipping point. That variable is a ratio. Every volcano holds its ground against the gas pressing up from below, and every edifice has a breaking point, a tensile strength that the rising pressure is trying to exceed. When the pressure wins, the structure fails all at once and the eruption goes explosive, as Pinatubo did. When the strength holds, gas finds a gentler route out, seeping through cracks and keeping the eruption effusive, the way St. Helens behaved in 2004. The threshold is not a fixed number. It shifts with temperature, with how fractured the rock has grown, with the changing chemistry of the melt. All that is knowable in principle. The uncertainty is whether St. Helens is sitting above that line or below it, and the difference between those two positions is the difference between a quiet season and a catastrophe. Monitoring instruments are spread across the mountain, each one watching one sign of pressure. But the mountain itself has a history of behaving in ways the instruments did not predict, and there's a complication no model accounts for. The glacier. Inside the crater sits the crater glacier, a young mass of ice that didn't exist before 1980. It grew fast, in the deep shadow of the blast walls, thickening by as much as 15 meters a year until it reached a maximum of 200 meters deep, a blunt gray horseshoe of ice and rock wrapped around the old lava dome. That much ice is not passive scenery. It blankets the vent, a cold lid trapping the heat that radiates up from the conduit, slowing the escape of gas and steam. It loads the crater floor with millions of tons of weight, bending the stress field beneath it. Remove the ice too quickly, and the sudden release of pressure could tear open the ground, flash water to steam, and hurl the crater rim outward. So the glacier is both sensor and actor. Its crevasses record the slow movements of the magma below, its meltwater carries the chemical whispers of rising gas, and its own behavior tells scientists more than their instruments can. But the glacier is also hiding something. The cavity. Ground-penetrating radar has now mapped what lies beneath all that ice, and the image is not comforting. There is a void down there, a cavity carved out of the rock by decades of rising heat, and it is not staying still. Year after year, the gap grows larger, the hot rock slowly eating its way upward through the shattered mountain. Think of it as a pressure vessel waiting under the glacier, sealed and filling. If the magma ever reaches it, the steam would have nowhere to go but out. That kind of explosion doesn't crack the surface gently, it fragments the edifice itself, blowing the mountain apart from within before a single drop of lava ever sees the sky. Which is why scientists are watching the harmonic tremor so closely. Harmonic tremor. Harmonic tremor sounds unlike every other earthquake. Where normal quakes are sharp and sudden, this one is a continuous, low hum, a vibration that doesn't stop and start, but simply goes on, sometimes for hours. It has a signature, a steady rhythm that repeats over and over, and seismologists read it as the sound of fluid on the move. Magma, or superheated gas, forcing its way through cracks, widening them, climbing. It is one of the most reliable precursors to eruption that exists. And Mount St. Helens has been humming like this, on and off, for 18 months. Each burst hands the observatory another data point, another clue that something deep below is awake and restless. But the tremor comes and goes without warning, and no one knows why. The valve hypothesis. One theory tries to explain the pattern. Imagine the conduit, the narrow throat that carries magma upward as a pipe with a natural valve, a bottleneck where debris and cooling rock periodically clog the passage. When the valve is open, the magma flows freely and the tremor falls silent. When it closes, the pressure climbs behind the blockage, building day after day, until something gives and the obstruction ruptures through. That cycle could repeat this way for years, a slow, arrhythmic heartbeat under the ice, or the system could reach a point where the rupture is not a relief, but a release, everything unblocking at once. And the rupture might not happen where they expect. The flank. So picture the flank of the mountain itself. The summit gets all the attention, every camera and seismometer pointed at the crater. But magma does not always choose the obvious exit. St. Helens has a documented history of flank vents, eruptions punching sideways through the edifice instead of straight up, and the current deformation surveys are mapping weak zones low on the north and south flanks, places where the mountain is already shouldering the strain. A breach there would not announce itself at the summit. The instruments watching the crater would sit silent while the fire moved somewhere the monitoring was never aimed. A flank eruption would bypass all the summit monitoring, and the warning time would be measured in hours. The lahar risk. The danger does not stop at the mountain's base. It travels. Lahars, volcanic mudflows, gather up ash, rock and meltwater, and race down river valleys faster than a car on the freeway, thick and gray and indifferent. In 1980, those flows poured into the Toutle River and filled its channels with sediment so deep that much of it still has not cleared, decades later. The valley is a loaded shelf, waiting for the next jolt to tip it loose. A new eruption would not need to be large to mobilize what is already sitting there. Towns 50 miles downstream would have minutes of hard warning, not hours of reassurance. And the sediment isn't the only thing waiting in the river valleys. The logs, thousands of trees, whole forests stripped by the 1980 blast, are still clogging Spirit Lake and the Upper Toutle. They float, sink, and rotate in slow circles, patient as anything. In a major flood or a lahar, those logs stop being debris and become battering rams. Engineers have built log booms and debris barriers across the waterways to hold them back. But those barriers were designed for the flows of a quiet recovery, ordinary floods and steady rain, not the surge a large eruption could generate. A wall meant for a storm is not a wall meant for a mountain. One big pulse of water and sediment could snap those anchors and send the whole tangle downstream at once, unstoppable and mobile, which is why the evacuation zones were redrawn in 2022. The zones. When they redrew the map in 2022, they didn't draw one line around the mountain. They drew 3. The red zone hugs the crater and the steep upper flanks, ground that could be torn open or buried in the opening minutes of an eruption. The orange zone reaches down the river valleys, where lahars run fast and far, and where thousands of people live. The yellow zone stretches wider still, covering the towns that could see ash fall like grey snow. Each ring carries its own trigger. Red empties on the first sign of real unrest. Orange empties when the water systems start to warm. Yellow waits because you cannot evacuate a region for a tremor that never comes. But evacuation assumes they'll get a warning. The warning time. In the best case, the mountain gives weeks. Escalating swarms, swelling ground, gas pushing up through new cracks, each day a little louder than the last, and time to move people out by the tens of thousands. That is the scenario the plan is built around. The worst case is shorter, hours, maybe less, if the system jumps straight from quiet to explosive, if the magma finds an open conduit and moves fast. In 1980 the signs were there, but they read them wrong. A bulge growing for 2 months while the north flank sat in plain sight. Today the instruments are far sharper, seismometers on the slopes, GPS that measures the mountains swelling a centimeter at a time. But the plumbing under St. Helens is more complicated than it was in 1980. More pathways, more unknowns, more ways for a quiet day to end abruptly. And there's one signal scientists are waiting for that hasn't appeared yet. The earthquake swarm. When magma finally breaks toward the surface, it does not come silently. The earthquakes come in swarms, shallow and tightly clustered, riding the magma upward, their frequency climbing like a drumbeat that never slows. It is a curve, and volcanologists watch it like a patient watches a fever. The rate doubles, then doubles again, quakes pressing closer together until they blur into a constant tremor. That crescendo, that steepening line, is the clearest warning a volcano can give. St. Helens has shown deep swarms in recent years, rumbles from far below that arrive and fade. But the shallow crescendo, the pattern that says the magma has cleared its throat and started climbing, has not come. Which means the magma is still deep, but the path to the surface is open. The conduit. Between those two earthquakes lies the conduit, a vertical pipe drilled by nature through layers of old rock. In 2004, magma rose into it and stalled there, cooling into a plug of solid lava that has sat for 20 years. Now the tremor suggests that plug is giving way, cracking and shifting under pressure from below. A conduit that stays open long enough stops being a question of whether and becomes a question of when. Once magma clears that last stretch, ascent can be startlingly quick. Hours, sometimes days, separate the first upward movement from the moment it meets the open air, and the distance it must cover is not far at all. And if the ascent is fast enough, it will trigger one specific type of eruption. Vulcanian. Volcanologists call it Vulcanian, after the island where it was first described. A plug of thick, sticky magma hardens in the throat of the vent, and gas trapped beneath it builds until the whole cap blows off in a single, cannon-like blast. Each explosion is separate, discrete, like shots from a heavy gun, and each one hurls chunks of solid rock into the air. Ballistic blocks the size of cars can land miles from the crater, thrown by nothing but pressure. St. Helens delivered these pulses in 1980 and again in 2004, short, violent bursts that ended almost as soon as they began. But the cavity and the conduit she has built since then could produce them on a larger scale. Violent, yes, but short-lived. But there's a scenario that's worse than Vulcanian. Plinian, named for the Roman writer who watched Vesuvius and described the towering plume of ash as if it were a pine tree. Here, the vent does not choke and explode. It stays open, and magma pours out continuously for hours on end. The column climbs not just into the sky, but into the stratosphere, 10–20 miles up, spreading ash across whole states as it goes. In 1980, St. Helens erupted Plinian for 9 straight hours. That sustained column is what collapsed into the pyroclastic flows that flattened the forest and raced down the mountain. A Plinian eruption at St. Helens is not a question of bigger explosions, but of endurance, of a vent that refuses to close. And the current magma supply rate is higher than it was in 1980. The column. Picture the column as a towering chimney of superheated gas, rising tens of thousands of feet into the stratosphere. Inside it, ash and rock are sorted by the wind the way a river sorts sediment, the heaviest grains falling out first, the finest drifting for days. A full-scale Plinian column from St. Helens would carry that ash on prevailing westerlies across Washington, Idaho, and into Montana. It would close airports, ground every flight in the region, and coat towns in a gritty gray snow that clogs filters and stalls engines. But the ash isn't the part that keeps scientists awake. Pyroclastic flows. The part that keeps them awake is what happens when that column loses its strength and collapses under its own weight. What comes down is no longer ash. It is an avalanche of gas, rock, and superheated debris moving at hundreds of miles an hour, hot enough to incinerate everything in its path. These are pyroclastic flows, and they are the mountain's most patient weapon. The 1980 blast was a single lateral surge, one violent sideways push. A full Plinian eruption produces something different, dozens of them, spilling off every flank of the volcano at once. Each one follows the terrain, pouring into valleys and ravines like fast-moving concrete, and the topography around St. Helens channels those flows directly toward populated areas. The simulations. The scientists have run the numbers on this. Their computer models track a collapsing column and send the resulting flow downhill, and the simulations are unsparing. The town of Cougar sits in a valley that funnels the flow straight to it, and the models put the first surge there in under 10 minutes. Spirit Lake Highway gets buried in 5. By the time any warning reaches a listener, by the time a siren finishes its first cycle, the flow has already crossed the ground between the mountain and the road. So evacuation during an eruption is not a question of speed. It is an impossibility. Safety rests entirely on leaving before the column ever collapses, on a warning that goes out while the mountain still looks calm. Which brings scientists back to the question of what will trigger the collapse. The foam. Picture the magma rising through a kilometer of solid rock, the pressure on it falling with every meter it climbs. And just like a soda bottle being unscrewed, the gas dissolved inside begins to bubble free. What's left is no longer liquid rock at all, but foam, a froth of gas-holding bubbles straining against the walls of the conduit. If that foam can escape, the eruption stays gentle, a slow venting of pressure. But if it's trapped, if the bubbles can't find a way out, the pressure builds until the whole mass detonates. Everything comes down to one property, permeability, how easily the gas can slip through the magma and reach the surface. And recent lab experiments suggest St. Helens dacite has unusually low permeability. The experiments. In labs, scientists take samples of that dacite and subject them to conditions straight out of the mountain's interior, crushing pressures and searing heat. They measure how quickly the gas escapes, whether the rock lets it pass or holds it in. And for St. Helens dacite, something striking emerges. As it degasses, it forms an impermeable skin across its surface, a shell that locks the pressure inside. The gas has nowhere to go, so it builds, and the rock grows more and more ready to shatter. It explains the volcano's temperament perfectly, why again and again its eruptions begin with an explosive onset rather than a gentle flow. The mountain doesn't just leak its pressure, it holds it, and holds it, until it has no choice but to let it out all at once. But there's one variable the experiments can't replicate. The crystals. Deep inside that rising magma float crystals, grains of plagioclase and pyroxene and amphibole, solid fingers threaded through the liquid. And those crystals change everything about how the magma behaves. Crystals make the magma thicker, harder to stir, harder for gas to move through, so too many and the whole mass jams to a halt. Too few and it flows freely, the bubbles streaming away before they can gather force. The balance between the two decides whether the mountain erupts softly or goes off like a detonation. And here is the unnerving part. No one knows the crystal content of the magma sitting below St. Helens right now. It cannot be measured from the surface, cannot be seen through kilometers of rock. The only way to know is to watch it erupt. Which is why scientists are studying the rocks the mountain already erupted. The tephra. What the mountain threw up in 1980 is not rubble. It is a record, layer on layer of ash and pumice, that settled the way a storm leaves snow, each stratum preserving a single moment of the eruption's life. Read the crystals and the glass and the bubbles trapped inside them, and you can reconstruct the magma's temperature, its pressure, its chemistry, the way it held its breath in the weeks before it moved. These deposits are a forensic archive of what was happening in the dark, far beneath, where no instrument could reach. And the forensics revealed something that didn't match the seismic record. The discrepancy. The ash says the magma sat in a shallow chamber for weeks before it erupted. The earthquakes only recorded days of shallow rumbling. Those two clocks do not agree. Which means the mountain was already holding its charge near the surface, quietly, while the ground beneath it stayed still. The instruments were listening to the wrong signal, or listening too late. A body of molten rock can wait in the shallows without a tremor, and no seismometer would ever know. If the same thing is happening now, the eruption could be closer than the data suggests. The blind zone. There is a depth where magma becomes nearly invisible to the instruments we place on a mountain, not because the rock is silent, but because its sound is too faint to rise above the ordinary noise of a hot, fractured edifice. Slow creep through warm ground produces weak signals, a whisper that blends into the wind and the settling rock. Our networks are tuned for sudden movement, for the sharp crack of magma bursting upward, not for the long, patient push of a body of melt. So there is a blind range, a band of depth where rising magma leaves almost no trace, and that's the range where magma finally stalls before eruption. The stall. Rising magma does not always reach the surface. At some depth, the melt turns as dense as the rock around it, and it simply stops, or the cold crust siphons away its heat until it thickens and sinks into stillness. A stalled body of magma can sit like that for days, weeks, even months, pooled and patient, giving off nothing. Then heat arrives from below, or pressure builds, and the same quiet mass remembers how to move again. This is the silent phase. No tremor, no swelling flank, no plume, just a growing weight in the dark, and scientists are watching the ground this winter for the smallest sign that the weight is waking. And scientists just found evidence of a stall zone beneath the crater. The gravity anomaly. Microgravity surveys work like a scale for the underground. Flee over the same patch of ground, season after season, measure the pull of gravity at every point, and a tiny change in that pull betrays a change in mass below. A dense slug of magma slipping into place pulls harder on the instruments overhead. Over the past year, The readings have compiled into a positive anomaly, a compact knot of extra mass sitting 1 to 2 kilometers beneath the surface, dense enough and warm enough to be fresh melt pooling in the shallow crust. The number is small, a few hundred microgals against the enormous baseline of the Earth. But it is real, and it is growing, and it sits exactly in the depth range where this volcano's magma has stalled before. But the anomaly is not directly beneath the crater. The offset. It sits offset from the summit, roughly 800 meters to the north-northwest, and that places it squarely along the plain where the mountain tore itself open in 1980. The old fractures from that collapse never fully healed. Magma may be finding its way into them now, slipping sideways out of the central conduit to pool along the broken ground, which would feed this volcano through a route nobody built instruments for. Every network that watches the summit watches a place the melt may never pass through. The flank, the shattered and rehealed north shoulder, could hold the next pressure building while the crater above stays silent. And if magma is moving through the north flank, the edifice failure risk spikes. The stress test. Engineers took the shattered north shoulder and ran it through stress models. They asked how much pressure the cracked rock could hold before it gave way. How many atmospheres of magma forcing up through the fractures would tip the edifice past its limit? The answer came back lower than anyone had hoped. The flank, once broken and rehealed, carries scars that never fully knit. An intrusion into that zone could drive the whole shoulder into motion with almost no warning, not years of quiet creep, but days or hours. They measure, model, and watch, but the collapse itself gives away little ahead of time. But there's an instrument that might catch it just in time. The tilt meters. Tilt meters are the quiet heartbeat of the mountain. Bolted to the ground, they measure the angle of the surface to a precision that feels absurd, fractions of a nanoradian, the shift a heartbeat would induce in the floor beneath your feet. Because when magma moves, it doesn't always shout, it leans. The ground above a growing intrusion tilts measurably within minutes, a slow, silent bowing of the earth that nothing else registers. St. Helens now carries 12 of them, a ring of instruments arrayed around the edifice, each one telemetering its data back to the observatory in real time. 12 points of silence, listening for a lean that shouldn't be there. And on a Thursday morning in March, 3 of them spiked simultaneously. The event. The spike lasted 90 minutes. 3 tilt meters, miles apart, all recording the same 15 microradian tilt to the northwest, then a slow, unhurried relaxation back to zero. No felt earthquakes trailed it, no cracks opened on the surface, but a tilt signature like that matches a shallow pressurization pulse, something swelling under the flank, then settling. In the observatory, the debate ran for days. Magma moving up through the old fractures, or simply hot water and steam rising through the same paths. The evidence was ambiguous, the readings too clean. In the end, they settled on fluid, water, the less alarming answer. It was plausible, it was calm, it was the kind of event you file away and watch. But the next event, 3 weeks later, was different. The second pulse. 3 weeks later, the mountain moved again. This time the tilt was bigger, the disturbance longer, and beneath it all, a swarm of micro-earthquakes chattered through the rock like a conversation held just out of earshot. The signature was unmistakable now. This was not steam, not settling rock. This was magma, moving upward through the shallow crust, pushing against the ground beneath your feet. And still it did not erupt. The ground settled, the quakes faded, and the mountain went quiet once more. But the magma did not go away. It sits there now, shallow, mobile, waiting. What no one says aloud is the pattern in the records. The first pulse was a tremor, the second was a demand, and the interval between pulses is shortening. The forecast. Put the 2 events together and a sober consensus emerges from the observatory. Eruption is now likely, not merely possible, within a span of months to years. A significant share of the scenarios begin with a lateral blast or an explosive opening, the kind that does not announce itself politely. The exact timing cannot be pinned down. Volcanoes keep their calendars to themselves. But the system has crossed a line. Each pulse of magma infiltrating the shallow crust is a trial run, a rehearsal for the one that finally breaks through. So the honest forecast is this: something is coming, and no one can say which quiet month will be the last. Every rumble from this mountain is now measured against that single question, whether the next one is the one that stays. What happens now? So what happens now is vigilance carried out in silence. A 24/7 observatory watch keeps eyes on the seismometers around the clock. Weekly briefings lay out the numbers for scientists and land managers alike, and the public alert level has been raised to advisory, a quiet official nod that the ground under your feet is no longer a settled thing. Crews are installing additional sensors across the slopes, hardening the network that watches every tilt and tremor. Notification protocols are rehearsed, call trees tested, evacuation routes reread by emergency managers who hope never to use them. But mostly, everyone is waiting, and here is the part that keeps the watch steady. A mountain, this diligent in its warnings, has given them something the world rarely gets: time. Time to watch, to listen, to be ready. And so the people of the valley sleep under a mountain that is awake. They have done everything they can. The rest belongs to the magma. The wait. There is a kind of peace that settles over a valley that has made its peace with the mountain. The schools still open each morning, the timber trucks still crawl the ridgelines, and the instruments keep their quiet watch. Decades have passed since the mountain last roared, and generations have grown up in its soft shadow, learning to read its moods the way their parents did. St. Helens is not an enemy. It is not waiting, and it is not angry. It is simply doing what a volcano does, the way a river runs or a season turns, and everyone living at its feet understands that the wait is not a threat. It is a practice, a long habit of attention that has become, almost without anyone noticing, the very shape of their lives. Legacy. Because in the end, that is what St. Helens has always been: a laboratory and a teacher and a humbling reminder that the ground beneath us is alive. The 1980 eruption rewrote everything volcanologists thought they knew, and every tremor you feel today is a quiet examination, a test of all the lessons learned since. And that story is not unique. It is the story of every volcano, every tectonic boundary, every restless planet up and down the cosmos. Every world with a molten heart is a world that waits, holding its breath in its own patient way.